This is section 7.3, volume, the shell method. In section 7.3, we talk about the shell method, and this is an alternative method for finding the volume of a solid. So instead of the disk method or the washer method that we learned in the previous sections. The shell method is called this because it uses cylindrical shells. And these are basically tubes. So what we want to do is basically find the volume of these tubes. So this picture down here kind of illustrates what's going on. So you can see the tube that we have, and we're going to have another representative rectangle just like we did before, where W is the width and H is the height of the rectangle, and P is the distance between the axis of revolution and the center of the rectangle. So that's important to notice that P is really the distance between the axis of revolution in the center of the rectangle. And that can be found by this. So it's P plus half of the width. So when we take this rectangle and we revolve it about its axis of revolution, we get this tube shape like you saw on the previous screen, which we will refer to as cylindrical shells. So, you know, kind of like when we had the washer method, we would have to find the inner radius and the outer radius. It's the same thing when you have this tube. We need to find the inner and the outer radius. So this information here is helpful. So the outer radius is going to be P plus half the width, whereas the inner radius is going to be P minus half the width. And if you look at the previous slide, you can kind of see that. So if we want to find the volume of the shell, we are going to take the volume of the cylinder, which is essentially involving the outer radius, minus the volume of the hole, which is essentially using the inner radius, which we have here and here. Once this is all simplified, you will find that this becomes 2 pi times the average radius times the height times the thickness. And this is the formula that we will use to calculate these volumes. So let's take a look at an illustration. So let's say we're starting off with this region here. And if we take this region and we revolve this about a line parallel to the x-axis, so if we take it and revolve it here, it goes round and around and around and around, we will end up with this shape here. So it's hollow like before, so we need to find the inner radius and the outer radius, which we will analyze using this here. So take a moment and just kind of visualize what's happening here. So now, if we have an infinite number of these rectangular regions or representatives, if we have an infinite number of them, that leads us to the integral, which we've discussed before. So this here becomes what we are dealing with. And the things that you'll need to recognize is this, and this. And I think these three pieces are helpful to be shown in the next slide. Okay, so this is the important thing. This is talking about the shell method. So to find the volume, we either have a horizontal axis of revolution or a vertical axis of revolution. So this information is horizontal, this is vertical. So let's first talk about this horizontal axis of revolution. If we have this horizontal axis of revolution, like the x-axis, for example, then our rectangle is perpendicular to the y-axis. So the rectangle perpendicular to the y-axis. That means that everything is going to be in terms of y. And if you look at our integral, everything's in terms of y. So you can either think of this as our rectangle being perpendicular to the y-axis, or our axis of revolution is parallel to the x-axis. So axis of revolution parallel to x-axis. If that's the case, it's in terms of y. So looking at this formula, this is still a circular shape, and that's why we have this 2 pi. And then the py, again, is the distance from the axis of revolution to the middle of this object, or rectangle. Hy is the length of it. And then delta y is the width. And remember, dy and delta y are very, very similar. It's basically the same thing. And then our limits of integration are from c to d. And again, those are y values. On the other hand, a vertical axis of revolution means we are going to be revolving about something like the y-axis. So our rectangle is perpendicular to the x-axis. If our rectangle is perpendicular to the x-axis, everything is going to be in terms of x. Another way to think of this is our axis of revolution is parallel to the y-axis. If that's the case, everything is in terms of y. Everything holds similar here. Now, p of x, one thing to mention, this distance here, p of x, you'll notice that when p of x will always equal x if our region is attached, if you will, to the y-axis. And I'll show you some examples of that. But these are the formulas that you'll want to remember. So let's go ahead and look at the next slide. All right, so here the information is given to you. It says use the shell method to write and evaluate the definite integral that represents the volume of a solid generated about generated by revolving about the y-axis. So if we are revolving about the y-axis, our rectangle is perpendicular to the x-axis, which means everything here is going to be in terms of x. Our limits of integration, our integrand, the whole nine. So that's one thing we need to recognize. Now we need to identify some different parts of our formula. So let's just recall what our formula states. The volume is 2 pi times the integral from a to b of p of x times h of x times dx. So we need to identify p of x. And remember, p of x is the distance from the axis of revolution to the center of our rectangle. Now, if you look at this, if you just think of this coordinate plane, this distance is just an x value. From here to here, it is x. We don't know what that x is because we will have an infinite number of these rectangles. So we're just going to keep it generic. So this means that p of x is equal to x. And this is what I mean by our region being attached to the y-axis. It is simply x here. Now we also need to identify what h of x is. Recall, h of x is the height of this. So this distance here. Now I could have a rectangle over here or one over here, and hopefully you recognize that the height is always y. So y is equal to h of x. Well, it turns out we know what y is. Y is 1 minus x. So we know that h of x is 1 minus x. Remember, dx is just our variable of integration, so that just remains d of x. The only other thing we need for our formula are limits of integration, a to b here. In this case, remember, we are dealing with x values. Our region is sandwiched in between an x value of 0 and an x value of 1. So my limits of integration are from 0 to 1. Let's go ahead and write this formula. We end up having 2 pi times the integral from 0 to 1 of px, which is x, times h of x, which is 1 minus x dx. The hardest part here is setting up this integral. Once you have this set up, you should be able to integrate this. It may be helpful to distribute this x and write this as x minus x squared dx. When you integrate this and plug in our limits of integration, you should end up getting pi over 3. This example involved revolving about the y-axis. The next example involves revolving about the x-axis. Okay, in example 2, we are given 3 functions, but we are not given the graph, so we need to come up with it on our own. So in this case here, sketching a quick picture of this, y equals 4x squared would look a little something like this. X equals 0 goes through the x-axis at 0, and y equals 4 goes through the y-axis at 4. So this here becomes our region of interest. Now we want to revolve this about the x-axis. So I'm going to take this shape and revolve it about the x-axis. And if you want, you can sketch in the reflection. And you might be able to recognize that this is a hollow shape, and the washer method could be used as well. But here we are asked to use the shell method. Now, since we're revolving about the x-axis, we have a horizontal axis of revolution. So that means that everything is going to be in terms of y. Another way you can tell is that our rectangular shape has to be perpendicular to the y-axis in this case. And since our rectangle is perpendicular to the y-axis, that means everything is in terms of y. All right, so from here, we need to identify p of y and h of y. And when I do, well, let's state our formula again. So in this case, since everything's in terms of y, I have 2 pi times the integral from c to d of p of y times h of y dy. All right, so from here, we need to identify p of y. And remember, p of y is the distance from the axis of revolution to the center of this rectangle here. So if we are trying to figure this distance out, this is either going to be an x value or it's going to be a y value. And in this case, P of y is equal to y. Oops. So P of y is equal to y. And that's helpful. Now you might be wondering, okay, well, we know what y is. We know y is 4x squared, and you're absolutely right, but remember, everything needs to be in terms of y, so it would be useless to rewrite this with x's in it. Okay, so that's one thing to pay attention to. Now we need to identify h of y. Remember, h of y is the height of this rectangle. Okay, so this distance is x. So we know that h of y is equal to x. Now that's a problem because we don't want x. So what we need to do is we need to take this and solve this for x so we know what x is. So the first thing I'll do is divide by 4. So I have y over 4 is equal to x squared, and then I can take the square root of both sides. Technically, I need this plus or minus, but I'm only interested in the positive side of this parabola, so I'll omit the negative for now. So this means that x is equal to the square root of y over the square root of 4, which is 2. So instead of replacing this h of y with x, I'm going to replace it with root y over 2 because everything has to be in terms of x. I'm sorry, of y. Okay, so plugging our information into our formula, we have 2 pi times the integral of p of y is y, times h of y, which is the square root of y over 2 times dy. Now, the only other thing we need are our limits of integration. So we need to identify what our limits of integration are. You may recall that in order to find our limits of integration, in this case, we're looking for y values. So we are going to integrate from here to here. And these y values range from 0 to 4. So those are our limits of integration. So now I think it would be helpful to simplify our integrand here and proceed. So recall that the square root of y is the same thing as saying y to the 1/2 power. So here, if I have y times y to the 1/2, remember I can add these exponents. So my volume becomes the integral from 0 to 4 of 1/2 y to the 3/2 dy. It may be helpful to move that 1/2 to the outside. So pi times the integral of y to the 3/2 from 0 to 4. And you should be able to integrate this. Remember, you'll add 1 to the exponent, so it's kind of like adding 2 over 2. When you add 2 over 2, you get 5/2, so y to the 5/2. If you divide by that, it's the same thing as multiplying by the reciprocal, and then evaluate that from 0 to 4. When you do, you should end up getting 64 pi over 5 for that volume. So that wraps up the final example really of the shell method that I'll illustrate. But now I think it's important to kind of be able to distinguish among the different methods. So looking at this, disc and shell methods are sometimes difficult to identify. So the disc method, I want you to remember that the rectangle is always perpendicular to the axis of revolution. So here, these two involve examples of the disc method. So notice that the disc method has rectangles perpendicular to our axis of revolution. Okay. The shell method, on the other hand, the shell method, our rectangle is parallel to the axis of revolution. Okay, so make sure that you are able to notice that. Now, in the previous example, I was kind of talking about how you could use the shell method or the washer method. Let's analyze that a little bit further. So in this example, it says find the volume of a solid formed by revolving this region that's bounded by these graphs about the y-axis. So if I have something like this, let's see. All right, here's our picture. If I have this graph and I chose to use the washer method, I would have to identify the inner and the outer radius. Well, if I do that, then two integrals are necessary because the distance from our axis of revolution to the inner radius and the outer radius, it's different, and I would have to use two different integrals, as you can see here. Okay, so the alternative method would be using the shell method instead. If I were to use the shell method, I would only need one integral because the shell method has rectangles that are parallel to our axis of revolution. So from here, we only need one rectangle, and it would be set up as shown here. So even though we can solve this using the washer method or the shell method, sometimes it's helpful to try to visualize the region and identify which method would require less work. And in this particular example, the shell method requires less work. This wraps up section 7.3.